All right, yesterday we left off going over Le Chatelier's principle and the effects of Le Chatelier's principle and how you can stress one side of a system, or you stress the system and it will tweak itself to react to that stress. That was the qualitative examination of equilibrium. The equilibrium constant is how we go over this quantitatively. And so we need to start with this particular, with a new definition of reaction rate. Okay, and reaction rate is proportional to the concentrations of the reactants. I'm sorry, proportional to the product of the concentrations, okay, of the reactants. Okay. Got that? All right, so here's how this works. The concentrations of the reactants, okay, we're going to write a new, we're going to use a new equation, a new chemical reaction in order to demonstrate this. And this is called the Haber process. All of these are gases. There's no plus there. Gosh darn it. Forget about that. 2H3, gas, plus 92 kilojoules per mole. There's no delta H here. I did not write delta H equals anything. By writing it here with plus 92, this would be exothermic because it's producing heat. Okay, heat is a product of the forward reaction. Therefore, the forward reaction is exothermic. Okay, conceptually, you guys should be able to equate the two of them. All right, but there's another way of writing this equation. And as far as our rate, as far as determining that this rate law is what it's called, the reaction rate, the proportionality, we're going to write this out kind of longhand, more as in a descriptive form of what's going on. This is N2 plus 3 H2s. You follow me? Okay. And then an NH3 plus NH3 plus energy. All right, and here is what we use for our reaction rate. The reaction rate of the forward reaction, then, we said is proportional to the product of the concentrations of reactants. Well, if we have multiple copies of one of the reactants, okay, we need to multiply all of them together. Those all factor into the product. So the rate of this is equal to some constant, which we don't need to worry about right now, times the concentration of the nitrogen times the hydrogen times the hydrogen times the hydrogen. Well, how would we write that? That would be this times that would be that concentration cubed. Okay, well, that's the same thing as doing, you're just writing the concentration of this reactant and then putting the coefficient as the exponent. You guys see that? Okay, this is why, because we multiply all of the products together, multiply all the concentrations together. All right, so this is the forward reaction. Okay, the reverse reaction goes the other way. Rate of the reverse is going to equal some constant. And these are the reactants for the reverse reaction. So it's going to be NH3 squared. Follow me here? Okay. That is the reaction rate. The equilibrium constant the KEQ is the equilibrium constant. And it equals the rate of the reverse divided by the rate of the forward. The rate of our reverse is the NH3, and the rate of the forward is this one up here, the N2, and then the H2 cubed. And these two constants, through the magic of math, these get wrapped up into this value here. That doesn't really matter what these are, because they'll just become part of this constant over here mathematically. And so we get a KEQ equals NH3 squared over N2 H2 cubed for this reaction. And this is our equilibrium constant. So, some interesting things happen with this. This number stays the same KEQ is a characteristic of any reversible reaction. Whenever you have reactions that are reversible, that they're going back and forth at the same time, and it reaches equilibrium, no matter what the concentrations are at that equilibrium, the KEQ will always be the same. If you do this to those concentrations, this will always be the same number for any particular chemical reaction every time. So we use this to our advantage. All right. So let's look at both of these here. If we were to increase the concentration of our ammonia, this would lead to a shift to the left, correct? Yes. According to Le Chatelier's principle, if we increase this, Le Chatelier wants to decrease that. To decrease that, it's going to make more stuff over here. Yeah? Well, let's look over here. If we increase this number, in order to keep this ratio still equaling our constant, if we increase this, we have to increase these guys, right? That makes sense? Right. And so because this has to stay constant, if this increases, these two have to increase. And vice versa. If I decrease one of these, this is going to have to decrease, which means it's going to shift in that direction. You follow? So this is the quantifiable, this quantifiably shows Le Chatelier's principle. All right? And so in the future, which you guys don't have to do in this class, you're not going to have to do this. But in the future, you will be dealing, when you take your next chemistry class, and everybody takes another chemistry class. In college, you'll probably have to take it. You'll have to deal with equilibrium, and you'll have to do this math. Okay, but this is the idea for it right now, is that this is the quantifiable version of Le Chatelier's principle. Okay, and so that's why we talk about them together. All you guys are expected to do is recognize this, that if you have any equation that is reversible and you have coefficients to it, the KEQ will equal concentration of C to the C times D to the D over A to the A, B to the B. Okay, and this is for anything. There are a couple of exceptions. And so before you guys go today, we need to go over those. Okay, solids and liquids are pure. And so you do not use them in this equation because they don't have a concentration. Their concentration won't change. You can't make, if you add solid metal, you can't increase or decrease the concentration of solid metal because it's pure. It is what it is. Right? If there's no dilution involved there. All right, so you don't use them in the KEQ. Okay. All right, this is really the exception you guys need to look out for. All right, that's it for KEQ. And that is pretty much it for equilibrium and reaction rate and this unit.